Okay.
Okay, we have opened the webinar so people can start to check their connections. We will be starting the program in about 1 minute. And for information, the webinar will be recorded, is being recorded. Shenshan, are you there?
Yes, Todd. It's me.
Perfect.
Okay, I will open the camera. Okay?
Perfect.
Yes. Hello,
Okay, hello.
everyone.
Hello,
Good
Tinchan.
morning. Good morning.
Afternoon.
Good afternoon, yeah, for you.
Yeah. For me, it's afternoon. For you, it's morning.
Very good.
So it's 9:30 and people are still coming in. We'll wait a few more minutes. It's a little over 60 people have registered, and we'll give them a few minutes to sign in. Okay, still waiting for some more people to connect, and we will start in 1 or 2 minutes. But it looks like there's still a number of people who have not connected yet. Okay, we will go ahead and start the webinar. My name is Todd Flack. I work in a small environmental NGO called Bellona. I'm based here in Oslo, Norway, as you can see by the language from my background banner. We've been working on CCS for quite a while, and we were given the opportunity to participate in the CHEERS project as responsible for dissemination. So we have set up the webinar for Work Package 2, who will be sharing their exciting results from their work so far. And I welcome everybody. I believe there's more people coming. The webinar is being recorded, and it will be placed on our YouTube channel afterwards. So you can share that, and other people who weren't able to attend can view that. We are planning for a rather compact format, about 1 hour and 15 minutes, and we're saving 10-15 minutes for questions and answers. So the QA button should be working for you, and you can type in your question at any time. Those questions will be visible to the panelists, and some of them will be able to answer them during the session. And when they're answered, they will be visible. So I would like then to give the floor to our Work Package 2 leader, Stefan Batlin.
Yes, thank you, Todd. I will share my screen. So can you see my screen?
Yes.
Yes.
That's
Okay,
good.
thanks. So good morning, everyone, or good afternoon, depending on where you are located. And welcome to this first webinar about the CHEERS project, which is dedicated to the design studies. So my name is Stéphane Bertolin. I'm the CLC project leader at IFP Énergie Nouvelle and work package leader in CHEERS. So some cheering friends will join me to present the result of this work package. So these are the Professor Sen Shanli from Tsinghua University in Beijing, in China, and Dr. Sina Tevianian and Catherine Laroche from IFP Énergie Nouvelle, who are respectively in charge of the technology design and process design for the CLC application. So as Todd said, this webinar will last 1 hour and 15 minutes. So we'll ask to keep your question to the end of the webinar to ensure that we will respect the time schedule. So I will start with the presentation. So what about the CHEERS project? So CHEERS is a Chinese-European project which aims at demonstrating the CLC technology at 3 megawatt scale, thanks to a demonstration unit which will be located in China. So this project brings together 9 partners, including 3 universities, so Tsinghua University and Zhejiang University in China, and Silesian University of Technology in Poland. It also includes 3 research centers, SINTEF Energy and SINTEF MK in Norway, and IFP Énergie Nouvelle in France, 2 industrial company, Dongfang Boiler in China, we will host the demonstration unit, and Total, so no Total Energy in France, and Bellona, which is a foundation in charge of the communication and dissemination for the project. So CHEERS is a 5 years project, both funded by Europe through the Horizon 2020 program and by the Ministry of Science and Technology in China. And the global budget is about 17 million euro, including about 10 million euro from Europe. So the main objective of the CHEERS project is to demonstrate a new second generation CCS technology at relevant size, which means for us evolve from TRL4 pilot units, which are basically the pilot units that exist in IFP or Tsinghua University or in SINTEF, to TRL7 scale, which is the last step before the industrialization of the process. So the main deliverable of CHEERS will be the design, build, and operation of this demonstration unit. And we will also intend also to provide a techno-economic assessment of the CLC process at industrial scale. So to achieve these goals, the project is organized in several work packages. The first one, work package 1, led by SINTEF, is for the coordination of the project. And then you have the work package 2 for design studies, work package 3 about development of the oxygen carrier. In fact, it's the selection of the oxygen carrier for the demonstration unit. Work package 4 is for the process integration. So basically, it corresponds to the feed for the demonstration unit. Work package 5 is about the assessment at the industrial scale. And the most important work package 6, led by Tsinghua, is about the operation, construction and operation of the demonstration unit in China. And finally, work package 7, led by Bellona, is about the communication and dissemination for the project. So today, we'll just focus on the work package 2, the design studies. So just to conclude this brief introduction and provide some information before the presentation of my colleague, just would like to highlight what was the biggest challenge for this work package. So as I said, CHEERS is a Chinese European project with a common objective, which is a demonstration of the CLC technology, but considering different purposes. So indeed, for European side, the application case considered in CHEERS is the production of steam and power in industry, for example, in the refinery, by using EV feedstock like petcoke, which is difficult to recover or recycle. On the other side, from Chinese side, the main application case is the power supply at large scale, considering lighter feedstock like coal or lignite. And this difference in the strategy has induced several differences in the design. So as we will see after. And it was a big challenge to combine these different requirements to provide a common design in only one demo unit and to comply with all of these requirements. So this will be explained more in detail by my colleague. And this is the agenda for the meeting. So first, Sina will present the European design from the design philosophy to the result from experimentation achieved on a cold flow model, which has been designed, built, and operates in the framework of CHEERS. Then Professor Li will present the Chinese design with the same philosophy. And at the end, I will come back to briefly present a brief overview of the main result of the pre-FEED study, which was the final deliverable of this work package, and the main input for the work package 4, which was the feed of the demonstration unit. And at the end, we should have time to provide some conclusion, to provide some current status of the project, and answer your question. So now I will let the floor to my colleague Sina, which will present the European design.
Thank you very much. So just okay. Oops. Should be fine right now, right?
Yes, it's fine.
Okay. So hello everybody. My name is Sina Tebianian. I'm a research engineer in IFP Energie Nouvelle, and today is my pleasure to present you the European design of CLC based on IFPEN and the Total Energies technology. So in this scheme, we are just showing the concept of CLC based on European design. So we can actually see the main parts, which are the air reactor, where and let me just take also my laser. So the air reactor, where we actually the air in contact with the oxygen carrier gets oxidized, and then once oxidization is finished, we separate it from the depleted air. They go to this intermediate capacity, which is called the dividing fluidized bed. The dividing fluidized bed can either send the solid back to the air reactor for a recycling and the completion of the oxidation, or can send also the oxygen carrier to the fuel reactor. In the fuel reactor, the oxygen carrier actually releases its oxygen, and in contact with the solid fuel, it enhances the combustion reaction. For fluidization and also for gasification, we use two streams that can be both steam and recycled flue gas, as you can see here. Once we have the gasification and the combustion, the solid fuel and the oxygen carrier, they're transported to the unit that we call the carbon stripper, and carbon stripper is used to separate the unburnt solid fuel and the coke from the reduced oxygen carrier. The unburnt solid fuel is then separated by this cyclone and sent back to the fuel reactor. for completion of a combustion, and the reduced oxygen carrier is sent from this line to a air reactor for closing the loop of a CLC. As you can see here, we are showing three elements that are called with A, B, and C, and these are actually L valves. They're pneumatic valves that are used for controlling the solid circulation rate in the unit. The solid circulation actually is a very crucial parameter in the unit, because it's not only the solid circulation, but also it can define the operating conditions of the unit. For example, if we talk about the L valve A, of course, it controls the oxygen carrier flow rate to the fuel reactor, but the solid flux is also the amount of heat that we are bringing from the air reactor to the fuel reactor for the combustion reaction. Therefore, we can use it also for controlling the fuel reactor bed temperature for the desired value that we have. The other one, the L valve number B, is used for oxygen carrier recycling around the air reactor, and that's actually used if we are not satisfied with the degree of oxidation of the oxygen carrier in one pass, and we want to control the concentration of the oxygen in the depleted air. Therefore, we can actually recycle a part of the oxygen carrier back to the air reactor in order to achieve the concentration of oxygen that we need in the depleted air. The last L valve, which is connected here with the letter C, is of course for controlling the solid flux back from the carbon stripper back to the air reactor, but also can be used in order to control the level of fluidized bed in the carbon stripper. As Stefan was saying, our carbon stripper has integrated a heat exchanger, and the level of the fluidized bed in the carbon stripper actually can define the amount of heat that we are going to extract. And therefore, with L valve number C, we can actually do this, this control. So just in this slide, we're showing the important steps that our group with Total Energies has been involved for the CLC development. You can see three phases. The phase one, which was between 2008 and 2017, was mainly on the lab scale R&D. We did some proof of concept and demonstration of our technology up to a scale of 10 kilowatt lab scale hot pilot. We did also some R&D study in cold flow prototypes of different scales of different units that I will show in the next slide, and also studied the synthetic materials as an oxygen carrier. Between 2017 and 2022, which is actually the project CHEERS, it was mainly on the industrial demonstration of the technology. That therefore we are actually designing and now actually we're going to the construction of a 3 megawatt industrial demo unit that can be operated in autothermal operation, but also integrates some other important parts of a CLC, which are actually integrated heat exchange and flue gas treatment, for example, based on DSOX and DNOx. Between 2022 and 2027, actually the commercialization of the technology once we demonstrated on industrial demo, and that one is actually the demonstration of the process in a 50 megawatt scale unit, and also integration of the carbon capture and storage chain in a refinery or petrochemical industry. So that's the European roadmap for CLC development. In more detail, our activity was to obtain a robust design of different sections through research and development. So the main sections that I mentioned before are shown in this scheme here. The air reactor, that in our technology is mainly a riser. And for that one, we studied its hydrodynamics through this cold flow mock-up that was of 18-meter riser. We also studied the solid circulation that I said that are controlled with L valves, and those ones were studied at different scale prototypes up to a scale of 1 megawatt. We studied also the carbon stripper with a compact and fast separator at two different scales. The concept was validated at 10 kilowatt cold prototype, but then was studied also in 1 megawatt cold prototype in order to obtain a robust design. The fuel reactor, as you can see it here, has two different sections. The bottom section is mainly for giving the residence time necessary for the gasification of the solid fuel. And once we have the gasification, we have this other section, which is in dilute transport section. So it's mainly in a pneumatic transport, is for combustion termination of the gases produced in the gasification. And also that one, we studied it in different scale cold flow mockups. And here you can see also the picture of some of the ELVAs or the loop seals that we use for the solid circulation. And here is just the unit that is a pilot, a hot pilot plant that is based on our design in our laboratory. Apart from the cold flow studies for the also for the technology, we also work on the oxygen carrier development, and for that one we have different analytic methods in order to characterize the kinetics and the physical properties of the oxygen carrier. As you can see, we have a TGA in order to study the chemical reactivity of different oxygen carriers that we develop or that exist in as natural ores. We also study the reactivity through the batch fluidization. So we have a batch fluidized bed in order to study the oxidation and reduction of the oxygen carriers. And also we study its mechanical resistance to attrition through jet cup testing. Once we characterize the oxygen carrier in our analytic instruments, then we actually study its real behavior in continuous pilot operation, as you can see here. So as Stefan was saying, as part of CHEERS project, we have also produced a prototype of our design. And the main objective, the main reason behind the construction of this cold flow model was that the reliable design and operation of chemical looping combustion depends on some parameters such as the stable and controlled solid circulation, hydrodynamic stability in fuel reactor and the air reactor, the adaptability of the heat exchange to the thermal power. So if we want to increase the thermal power, we have to increase also the capacity of the heat exchanger and also the efficiency of oxygen carrier and solid fuel in the carbon stripper. We have decided to build an equivalent of 1.5 megawatt cold flow model that this time actually integrates all the sections of our design together in one unique cold flow model. What we have studied until now was actually to study and characterize individually each section of the design. This time we are actually integrating all together in order also to show that the design is stable and is robust, and the operation is stable and can be operated for long hours. And we studied this did some experimentation in order to characterize the fuel reactor hydrodynamics, to show the solid circulation control between the air reactor and the fuel reactor in the continuous operation, to study also the transport of oxygen carrier in air reactor, and also to show the carbon stripper efficiency. And I will show some of the results in this presentation. Okay, so here I'm just showing the time frame that actually involved the construction. This was a collaboration, of course, between Tsinghua, IFPEN, Total Energies, and Dongfang Boiler. So we were all part of this design. We had the meeting in Lyon in 2018, and then through we did some detailed design. We did the construction, the commissioning, different rounds of experiments in order to optimize the system of measurements and also the design. And finally, in the end of 2019, actually, we did a successful round of experiments for obtaining different experimental design. You can see a picture of the unit here. These are just some of the notes that we were taking during the meetings with our other partners. And here is just a picture of the group that we were working on during the commissioning. Okay, so the geometry is as I said, is really very close to the demo unit that we are doing in terms of the characteristics. We have an air reactor, is 10 meters high riser with a square section of 0.25. Then the solid flows to the dividing fluidized bed, different L valves, one for recycling back to the air reactor, and the other one to be sent to the fuel reactor. Different sizes also were used in order to see also the effect of the size of the L valve. The FR dense section that is actually used for mainly for the gasification was 2.5 meters high, and the cross section of 0.6 per 0.6. Then this one was connected through a riser to this carbon stripper that had the 3.9 meters high, and we had equipped the whole unit with pressure taps and also the possibility to do some deep lake filling for characterizing the hydrodynamics and the solid circulation. Okay, and the operating conditions, of course, the pressure of acquisition was 1 Hertz. We use sand particles with these characteristics. They are very close to the oxygen carrier that we think that to be used in the real unit. And we studied the hydrodynamics of the air reactor and the fuel reactor with a wide range of solid circulation between 0.14 to 4.7. We studied also the fuel reactor hydrodynamics with different superficial gas velocities between 0.7 to 1.5, and also the riser between 5 to 10 meters per second air reactor. So in this slide, I'm going to show you a visual behavior of the cold flow model, and you can also find this video on our CHEERS YouTube channel. Okay, so from the qualitative part, now we jump to the quantitative results. Some of the results I will show here. This is the air reactor. So as I said, the solid circulation was controlled by L valves and measured by DFB cyclone diplex solid accumulation. In this graph here on the bottom, you can see the riser solid mass flux with the different L valve variations that actually we can increase the solid circulation with the L valve variation, but also it depends on the superficial gas velocity in the riser because of the pressure the pressure drop in the riser. We also studied the maximum capacity of the riser, of the gas at a very low superficial gas velocity, and you can see that the pressure drop actually at a certain solid flux increased significantly, which corresponds to the maximum capacity of transport of the gas in that condition, which is the choking condition that should be avoided for a stable operation. We also studied the fuel reactor at different superficial gas velocities and solid circulation. Here you can see at 1 meters per second with two different solid circulation, 0.6 and 1.6, the axial bed density of the unit. And of course, we have more bed density when you increase the solid circulation because of the more concentration of solid in the freeboard of the unit. We also studied the average pressure fluctuations at different superficial gas velocities, and this value was very important also for the design of the demo unit in terms of the vibration and the mechanical stress on the structure, and that was actually used for this design of the demo unit. We also studied the carbon stripper. The carbon stripper efficiency actually we need to collect all the big large particles which represent the carbon stripper, the oxygen carrier, and let the finer particles which are mostly the solid fuel to leave the carbon stripper. We saw that the diameter of solids at the bottom of carbon stripper was independent of the operating conditions and around 350 micron. The fines were that were collected on the top of the carbon stripper between 120 and 200 micron, and the most important thing is that the particles smaller than 105 micron in the bottom section were less than 2%, which means that the carbon stripper is actually efficient at 98%, and we do not have a lot of solid, which is actually the unburnt fuel that leaves the fuel reactor and goes to the air reactor section, decreasing the carbon CO2 capture efficiency. Here I just wanted to say also that we studied the cyclone at different operating conditions with different pressure drops for the air reactor and the fuel reactor, and the results are going to be published in the future. So as conclusion, the several years of R&D activity resulted in a successful design of CLC concept based on IFPN and Total Energies technology. The cold flow model of the entire unit demonstrated the stability of the design in a wide range of operating conditions. We built a comprehensive database that will be published in the future, and also the experimental results represent an interesting challenge for CFD modeling that we have been involved in order to test the reliability of CFD. So thank you very much, and here is my also contact if you want to other questions. Thank you for your attention.
Okay, thank you, Sina. Thank you very much. So now we will let the floor to Professor Li from Tsinghua University to present the Chinese design.
Yes, Stefan, I'm here. I will share my screen.
Yes.
Perfect. Okay, Stefan, you can see my
yes. Yes, that's
perfect. Okay. Good morning, everyone. My name is Zhenshan Li from Tsinghua University of China. Now I will introduce the Chinese design of CLC demonstration unit inside the CHEERS project. The outline of this presentation includes first design principle and then the material selection and design result. Finally, the final section is cold flow model result. First, I will introduce a very short about our research activity of CLC in Tsinghua. Actually, we studied the research of chemical looping from 2002. We had built a flow databed TGA for kinetic study, include both reduction and oxidation of kinetics of oxygen carrier and char gasification. This method can reduce the mass transfer and heat transfer resistance, and can get more accurate kinetics. And then we built 1 kilowatt thermal input of CLC unit, and then 30 kilowatts thermal input of CLC units. Recently, we have built a 100 kilowatt thermal input of CLC unit. The total height is 20 meters high. So in this height, I think will be suitable to study the unburned gas conversion. Inside CHEERS project, we built a 1.5 megawatt cold flow model. I will introduce the result in next section. And now we are focused on the 3 megawatt demonstration unit in CHEERS project. In next step, we will focus on the 30 and 50 megawatt chemical looping in China, mainly coupled with coal-fired power plants, and we want to apply the chemical looping combustion technology in real market for commercial application. The research will focus on the reactor, solid circulation, oxygen carrier material, solid fuel conversion, autothermal operation, carbon capture efficiency. For CHEERS project, for the design, for the aerator is normal design. For example, the aerator has a dense zone dense zone at bottom and a dilute phase in the up section. The residence time of oxygen carrier should be enough for the oxidation. Of course, this will depend on the oxidation kinetics. One important thing is the solid circulation rate. Considering the matter balance and heat balance, a very high solid circulation rate should be achieved. So we, based on this requirement, design a reasonable hydrodynamics. For example, the gas velocity, particle size should be carefully selected to achieve enough solid circulation rate. Of course, we also consider how to extract the heat from aerator, because in aerator, a lot of heat will be released from oxygen carrier oxidation. In order to control the circulation rate, we divide the R into primary R and secondary R for the aerator. For the fuel reactor, this design is as shown in this slide. The bottom fuel reactor is tubulin bed and connected with a riser, and then in the up section is the carbon stripper. But this carbon stripper is used for European style design. It's used to separate char from oxygen carrier. The residence time in bottom should be enough for char conversion because char conversion is slow compared with oxygen carrier reduction. Residence time in riser and in carbon stripper should be high enough for the unburned gas conversion. In Chinese design, the solid circulation is achieved by overflow. Overflow port is located here in the middle of the fuel reactor. The height will be about 3.5 meters high. So the particles, the oxygen carrier will flow from fuel reactor into a loop seal through a overflow port. The coal. The solid fuel is fed into the dense bed by a two-stage of screw feeder system, as shown in this slide. This figure shows the total system of Chinese design. There are 4 main control loops. First, the pressure drop aerator here is controlled by the primary air flow rate and secondary air flow rate. the solid circulation rate is controlled by the secondary airflow rate. If the bed level is not enough for the fuel reactor, we must add enough solid into the fuel reactor bottom in order to achieve the overflow principle. So this is very important for Chinese design. The fuel reactor should be filled in with enough oxygen carrier. If the oxidation degree of oxygen carrier not enough, some oxygen carrier will be divided into from this loop seal and then return back to air reactor. I didn't show here, but we have actually some method to achieve this purpose. For the material, for solid fuel in China design, the lignite is used as shown in this table. This is the analysis of lignite. Because lignite has a very fast gasification kinetics. As shown in these figures, we did the gasification test of lignite for different size, particle size. We found if the particle size is more than 1 millimeter, the gasification kinetics is okay for the fuel reactor, for the gasification. For the oxygen carrier, there are 2 titanium ilmenites. Finally, we select the new alternative material for test in the demonstration unit. We also test the kinetics of this ilmenite oxygen carrier as shown in this figure. For oxidation reduction, we can find for the oxidation of ilmenite, the initial stage is very fast. The oxidation in the first stage can be finished within 5 seconds. So this means if we can make use of this stage, the residence time of oxygen carrier inside air reactor should be very short. For reduction for ilmenite will require at least 100 seconds. So based on this information, we did some calculation and design of the whole process. For example, I will not introduce in detail. For example, we calculated 11 cases from 2.4 megawatt to 4 megawatt for different thermal input and different operational parameters. For example, for the hydrodynamic features, we can calculate how much of solid particle along the reactor height. You can see the solid fraction in the up section is actually higher than that of traditional CFB boiler. The total pressure drop is about 21 kilopascal. This bad inventory is enough for the oxygen carrier oxidation. And this figure shows the solid fraction distribution along fuel reactor. You can see here there are a lot of solid particles at bottom of fuel reactor. So in order to ensure the overflow. For the oxidation time of oxygen carrier, because we found from the 0 to 60% of oxidation is very fast. So we think it may be not necessary for oxygen carrier to get 100% conversion, because actually for the chemical looping we just need delta X. Delta X means delta conversion. So we can select the oxygen carrier reaction at the very fast reaction stage. So in this case, the residence time for reactor can be short. We also calculate how about the carbon capture efficiency change with, for example, the residence time, the carbon stripper efficiency. We found for lignite, even without carbon stripper, we can also achieve the 90% of carbon capture efficiency, because lignite is very reactive solid fuel and has a very fast gasification kinetics. As shown in CINA, we also did the cutoff flow model test for our design. these values are totally same with what shown in Sina's presentation. I just show some results. In our test, we have used 3 different particle size of sand, and also measure the solid circulation rate, solid fraction, and residence time. As shown in this figure, the pressure drop we measure a long time. Some variables, for example, the pressure drop of different reactor for a very long time. You can see here. This result indicates the operation is very stable. And also for the solid circulation is also stable. And then we studied the particle distribution at different equipment. So we found most particle are located at the fuel at the bottom, the tubulin band, as shown in this here. Because the fuel at the bottom is very large, so it requires a lot of solid particle. I also studied the turbulent gas velocity at different operational parameter, because this is a very important parameter for turbulent flow design. We found 4 different particle sizes. This turbulent this transition from bubbling to turbulent fluidization different. So based on this experiment, we get these numbers for design. We also measure the solid fraction along the fuel reactor. You see here, at different height. At the bottom fuel reactor, this is the typical turbulent flow design. But at above some height, the solid particle is not too much. Is the dilute phase. So we also study the overflow port here, because in Chinese design, the overflow is very important to control the solid circulation flow rate. So we want to know how to design, how to predict the circulation rate from overflow. So we did a lot of tests and developed the model shown here. For different fluidization zone. And the test result indicates the overflow model can predict the solid circulation rate accurately. The error within 25%, enough for the engineering design. We also studied the hydrodynamics of aerator. You see here, the circulation rate change with the aerator gas velocity. Of course, is very reasonable. The circulation rate increase with. Sorry. There is a big rain outside, so I closed my window. So you can see the solid circulation rate increase very fast with the gas velocity. But we found when the gas velocity is higher than 8 meters per second, the solid circulation rate is stable. It doesn't change too much. We also found the pressure drop of aerator in the dilute phase. It depends on the circulation rate, as shown in this graph. So based on this finding, for the demonstration unit, we can measure the circulation rate based on this pressure drop. If we do some calibration at lower temperature, so based on the pressure drop along different height of aerator, we can measure actually the circulation rate, because for the fluid bed at high temperature, not easy to measure the circulation rate. But circulation rate is very important for the chemical looping combustion of solid fuel. Based on all about the result, we finally summarize these two figures. We want to get the reasonable operational zone for the solid fuel chemical looping, but also some result from different research institutes also put here. So we found in order to achieve the autothermal operation of chemical looping unit, the solid circulation rate must be higher than 25 kilogram per square meter per second, as shown here. So in our design, based on the design result, also the cold flow model result, the value of solid circulation rate are larger than the 25 kilogram per square meter per second. Yeah, here located here. So based on this result, the solid circulation rate will be enough for the autothermal operation in next step for the demonstration unit. We can also look at the residence time in the fuel reactor, because this residence time is also important for charge conversion. In our design, the residence time is changed between 200 and 300 seconds. And we think this residence time is enough for the lignite charge conversion. So yeah, even at a not a very high temperature, we can also achieve more than 80% of carbon capture efficiency. Finally, is the summary. In Chinese design of chemical looping demonstration unit, the overflow principle from fuel reactor to air reactor is used to control the solid circulation. Oxygen carrier is returned back to fuel reactor riser into the dilute phase, is used to convert the unburned gas inside the riser and carbon super. Primary and secondary are used in air reactor to control the heat release ratio, and also used to control the solid circulation rate. Fuel reactor is designed as a tubulin bed connecting with a riser, and hot outside oxygen carrier return back to fuel reactor riser to convert the unburned gas. All these designs are validated by the cold flow model. In our design, high reactivity of lignite with low sulfur, low ash content is selected as the design fuel. We will feed the solid fuel into the gas bed of fuel reactor. Ilmenite is selected for the oxygen carrier. The thermal input between 2.4 megawatt to 4 megawatt. Finally, the CO2 purity will be designed as 97%. Carbon capture efficiency will be higher than 90%. The thermal efficiency will be 30 to 70%. That's all. Thank you for your attention.
Thank you, Sanchan. Thank you. Okay, so now that each design has been presented in detail, I will just provide a brief overview of the pre-FEED study, which was the final deliverable of the work package 2, and the main input for the FEED. So, so these are the main requirements we should meet for the demonstration unit. So just to remind you, we need to implement two interchangeable configuration. So just to remind you the difference between two designs, the same scheme. So here you have the Chinese configuration. So it's the same scheme that was just described by Zhenshan. So here you can find the carbon stripper, which is located beside the fuel reactor, with an exit from the fuel reactor with an overflow here. And this is the European design with the carbon stripper located at the top of the fuel reactor riser here, and the divided fluidized bed, which allows us to recycle a part of the oxygen carrier to the air reactor to control the oxidation rate of the oxygen carrier and operate with a control airflow rate in the air reactor. So this was the first requirement for the design. The second one was to be able to assess a wide range of operating conditions, which means, for example, to operate with a thermal input which can vary from 50 to 100%, which means in our case from 2 to 4 megawatts, considering that 3 megawatts is the nominal case. Regarding the oxygen carrier, we also intend to operate with different conditions in terms of oxygen transport capacity, of density, and oxidation states of the oxygen carrier. Regarding the fuel, we have considered natural gas and biomass for the startup, and petcoke and lignite for the operation. So finally, we have produced 23 design cases, which have been fully calculated to reach the operational limits of the process for the feed. So it was really a huge work to produce all of these heat and material balances for many cases. And finally, the last requirement was to provide a design which is representative of a large-scale unit, which means to be able to reach a high carbon capture efficiency, to have an autothermal operation, considering significant heat losses. So in our case, we have considered 20% heat losses, and also to put in the units refractory that can be used at industrial scales. So for that, a site study driven by Total Energy was conducted with a French company specialized in refractory materials. So this is the block flow diagram of the demonstration unit, including the reaction section in the middle and all of the peripheral sections which are needed for the operation. So as you can see, most of the utilities are located outside the battery limit because they are already existing in the Dongfang site in Deyang. But we need to provide a design for all of this peripheral section inside the battery limit, like the air supply with the air blower, the oxygen carrier and solid fuel storage and injection into the unit, the production of steam for the fuel reactor, some heat exchange between the capacity inside the reaction unit and cooling water, the flue gas recycle, the bottom solid discharge from each reactor, and the flue gas management to remove SOx, NOx, and dust from the flue gases. So now I will just focus on the main part of the design, which is the reaction section. And this section has been fully described through a process design package, a PDP. So here you can see the main content of this document. So the first point was to remind the basis of design for the demonstration unit. So basically it was the requirements for the design. Then we provided a complete description of the process in each configuration. Then the heat and material balances for all of the design cases. And then the supply specification for the process. For example, here you have the specification for the solid fuel with the composition. So as you can see, there is huge difference between petcoke and lignite in terms of carbon content or ash content or volatile, which explains the difference in design. Here you have the fuel consumption depending on the operating case, nominal, minimum, and maximum case, and on the feed considered. And regarding the oxygen carrier, so as Setchan said, we have considered ilmenite as the oxygen carrier. So here you have its main properties in terms of density, particle size, and the composition. And for the unit, the total inventory is about 30 tons. We also provide results from about the effluent and wastes from the unit. So here you have the composition, temperature, and flow rate of the flue gases from both the air reactor and the fuel reactor. And also the solid waste, so char, ashes, and oxygen carrier. So as you can see, there is a huge difference between the minimum and maximum oxygen carrier flow rate considered in the studies. It's because we have made some assumption on the lifetime of the oxygen carrier and consider the worst case where the lifetime is very short. But it's just for the design. We hope that the lifetime will be much better than this what is given by this figure. Then we also provide some standard for the engineering company, a description of the control loop for the operation of the unit, electricity consumption. We also perform first ASOP to prepare the acid in the feed. We have provided a preliminary plot plan. Oh, sorry, I forgot to mention this part. Yes, sorry, this is regarding the equipment list and specification. So I forgot to mention that we have provided a process data sheet for all of the main equipments. So here you have, as an example, the process data sheet for the air reactor and one loop seal. So on this document, we provided the internal dimension of the equipment and all of the sensors and sampling which are needed for the experimentation. So I go back to the plot plan. So here you have a short map of the DBC facility in Deyang in China. So this area will be allocated to the project. So you can find it here with the main dimension. And here you can see the location of the main equipment of the demonstration unit with the size. And the total elevation for the whole unit is about 45 meters. And finally, we also provided some drawings, especially a process flow diagram for the unit. So for example, here you have the PFD for the main section of the unit, so section S100, in which you can see the main equipment, the air reactor, fuel reactor, the carbon stripper for the European configuration and Chinese configuration. We also provided here the main control loop that you can see here for the control of the process, and the solid and oxygen carrier fuel inlet and solid discharge. We provide the same kind of documents for the flue gas treatment that you can see here. So here you have the exhaust of the flue gases from the air reactor and the fuel reactor. So in CHEERS, for the polishing of the flue gas from the fuel reactor, we just mixed, in fact, flue gases from both reactors in the mixing chambers to proceed to the combustion of the unbound compound with the air which is in the air reactor depleted air. So it is in this part. And then we have a backpass which include DINOX, DSOX, and the cooling of the flue gases. And at the end, DDoS section before sending the flue gases to the chimney. And this part is for the recycle of the flue gases from the fuel reactor with a small backpass to cool down the flue gases, a DDoS, and here a compressor to be able to recycle the flue gases to the fuel reactor and carbon stripper and other equipment. So that's what I wanted to show for the pre-FEED study. So now to conclude with the presentation, I will just provide a short sum up of what we have talking about and the current status of the CHEERS project. So just to sum up the main achievements of this work package 2. So we have provided a 3 megawatt CLC demo unit design at pre-FEED stage. So it was a challenging multimodal design because it included 2 different configurations. We also design, built, and operate a cold flow model at the size of 1.5 megawatts in both configurations. So for doing that, we have developed a set of design tools which are now available for designing a CLC unit at industrial scale. And last but not the least, we can say that this work package 2 was a unique and successful collaboration between China and Europe for CLC CCS, as we have succeeded in developing this process. So what is the current status of CHEERS? So actually, this pre-FEED study was delivered end of 2018, so with 1 year delay. So this delay was mainly due to the complexity of the design and also to the design, construction of an operation of the cold flow model, which was not expected at the beginning of the CHEERS project. So then the next step is the FEED study in work package 4, which is led by TotalEnergies. So this FEED study has been conducted from mid-2020 to May this year. And the current status regarding this FEED study. So today the FEED is completed. A first cost estimate has been provided by the engineering company. And this cost estimate is currently updated by Dongfang, considering the Chinese market. And the final investment decision is expected by the end of July, based on this last cost estimate. So next, so we are mid-2021 here. So the next phase will be the EPC phase. So it will be driven by Dongfang and led by Tsinghua University. So this EPC phase will be about one year to provide the demonstration unit. Then we will have a short time for the startup of the unit and 2 different operation phase, one in European configuration and one in Chinese configuration. And then the end of the project is expected by September or October of 2023, with a 1 year delay compared to the initial schedule. Just one short word about progress in the other work packages. So regarding the work package 3 about the oxygen carrier selection. So after a first screening of material by SINTEF MK at lab scale, 3 candidates have been benchmarked in a pilot unit, both at SINTEF and at IFN. And then the current status is that an ilmenite has been selected for the demonstration unit based on its good performances in terms of reactivity and lifetime. And regarding the work package 5, which is a techno-economic assessment at industrial scale, So for this study, we have considered two different design cases. So one for the refinery case and one for the power application, and two reference cases that will be considered for the benchmark with the CLC technology. So the first one is NGCC technology and amine for the CO2 capture. The second one is the CFB technology and the CO2 capture with amine. So finally, we will have to provide 6 design cases for this work package. So for 3 technology and 2 design cases. So the current status for this work package. So all of these process simulation are now completed. And Total is going to perform a call for tender for the cost estimation of all of these design cases. So thank you for your attention. There are 5 minutes left to answer your question. So please feel free to raise your hand. I don't know if there is a question in the chat. I don't know, Catherine, if you have followed the questions.
No. There is no question up to now, so don't
Okay.
hesitate, and we'll be happy
There
to
is one
answer you.
question in the chat.
Oh, okay.
Oh, you have one? So maybe
one.
I have some problem because I don't see any.
So maybe I read it. There is
Yes.
So it's any consideration for A, drying of lignite, and B, potential fragile nature of lignite or its attrition and consequent effect on the carbon stripper design. I think it's mainly for that.
Yes, it's mainly for Professor Lee.
Yes. This comes from Sanka. From Australia. I'm not sure. Yeah, for drying of lignite, actually we didn't consider the drying of lignite, but normally the original lignite is very white. We normally in China for the combustion of lignite normally put the lignite outside the room for some days with sunshine. So by this method, a lot of water will be evaporated, and then there will be a seal process, and then put the lignite directly into the fuel reactor. For the second question, potential attrition for lignite. Yeah, you are right. The lignite is very easy to be attrition fragmentation. Yes. We also want to make use of these features and want to make the lignite become smaller and smaller, and then the ash will fly from cyclone in a way of fly ash. So in this way, we want to avoid the discharge of big ash with oxygen carrier in order to avoid this problem. Because if the ash particle is very big, we have to discharge the ash from the bottom fuel reactor. By this way, there will be a lot of oxygen carrier also discharged from bottom. So we want to make lignite ash leave the system in a way of fly ash. So this depends on the attrition rate of lignite ash. But based on our experience, it's very easy for lignite ash to attrition in a very small particle size. And yes, yes, this will affect the carbon stripper design. Yes, but as what I said, even without carbon stripper, for lignite, the reaction time of fuel reactor is also enough for lignite charge conversion. So for lignite solid fuel, we think is okay. It's okay for the carbon stripper, even without carbon stripper. Okay, I'm not sure if what I say is okay for you.
Okay, thank you, Zenshin. So we do have 2 more questions. So one from Anders Lingfeld about the oxygen carrier. So what was the synthetic oxygen carrier that we mentioned initially?
Yes,
So,
I think Anders, you were thinking about the presentation from Sina, the IFPN4 presentation. So the synthetic oxygen carrier is basically a copper oxide on alumina. So it's an in-house formulation at IFP Energy Nouvelle. But we do not implement this oxygen carrier into the CHEERS project. So maybe it will be tested after the project, but not in CHEERS.
okay, thank you, Stefan. So we have also a question from Jochen Ströhle. So what will be the particle size of the fuel in the 3 megawatt plant? So that's from
Sina, can you?
There are 2 actually.
Yes,
we
it depends on the.
Yeah.
Yes.
It depends on the operation. So for European design, we work on the Geldort B particles. So it will be around between 250 350 microns. And for Chinese operation, maybe Professor Lee, you can answer.
Yeah, for Chinese design, the particle size field will be about 1 millimeter for lignite, something like that. The average solid fuel particle size will be 1 millimeter. Because from our experience, it's okay for the lignite to feed system with 1 millimeter. If the size is smaller, we have to use a milling system. But for CLB operation, for example, Dongfang Boiler Company, they had a lot of experience to feed the several millimeter particle size into the CLB boiler. This is the first reason. The second reason why we use larger particle size, we want to put the big size particle into the bottom of the reactor, because as shown in the proximate analysis of lignite, there is a lot of volatile. For lignite, the volatile content is very high. If we use the big particle size, the particle will go down into the bottom, and then there will be enough contact between volatile and oxygen current. So by this way, we want to convert the volatile as high as possible. So this is the second reason for why we select the big size of lignite for solid fuel. Okay.
Thank you, Zenshin.
Welcome.
I don't see any more questions, and I think time is already running.
Yes.
So
Okay. Thank you, Catherine. So
there is maybe one last question about L valves. Are you sure L valves will work in industrial scale? I thought there was a size limit. So a question from Anders.
Yes, so actually the L valves that we are going to test on the 3 megawatt, they're already a very we actually chose them also in order to be capable of handling a very high amount of solid flux. Of course, for the industrial scale, there is we need some other considerations, and we cannot go in infinity, and we have to optimize their design in order to be able to have the same kind of behavior. Based on what we are doing in the cold flow model, we are also doing some CFD modeling, and based on also the 3 megawatt results, we can actually optimize the design for the industrial scale.
Okay, thank you, Sina.
Okay, thank you, Sina. Thank you all for your question. So just to conclude with this webinar, so there are some links to social media if you want to follow the CHEERS project. And new webinar about other work packages are coming soon to present the result of our work. So thank you all for having attended this webinar, and I wish you a nice day. Thank you.
Thank you very much.
Well, thank you, Sarah.
Thank you.
Thank you.
Bye.
Thank you, everyone.
Thank you, panelists. Work
See you
package group.
later. Bye-bye.
Thank you. Goodbye.
Bye.
Bye-bye.